All X-ray tubes have a cathode. The cathode creates free electrons through the process of thermionic emission. You should also know that the cathode is negatively charged. This makes sense because the cathode is the source of these negatively charged electrons. The next major component of the X-ray tube is the anode. The anode absorbs electrons and creates X-rays. The anode is positively charged. This makes sense as the anode attracts the negatively charged electrons from the cathode. You can remember the charge of the anode and cathode like this. You want an A+, not a C- in X-ray physics. The next part of the X-ray tube is what we call the glass envelope. The glass envelope creates an air-free vacuum around the cathode and the anode. This is important to protect the tube from oxidation and corrosion. Without the glass envelope, the filament would quickly corrode and burn up. X-ray production would no longer be possible. The glass envelope gets very hot during X-ray production, so it's constructed of a special material called borosilicate glass, also called Pyrex glass, which is very heat tolerant. Sometimes the envelope isn't made of glass at all. Some machines use metal or ceramic. The last major component of the X-ray tube is called the tube housing, sometimes called the metal housing or the lead housing. The purpose of the tube housing is to prevent X-rays from being emitted throughout the exam room. Basically, it absorbs all the X-ray photons except those that are being aimed towards the patients. The tube housing must be designed to keep leakage radiation to a maximum of 0.88 milligray per hour when operated at maximum technical factors. So let's look at a few of these components in detail. The cathode assembly is the negatively charged side of the X-ray tube. The cathode itself is actually a small tungsten filament. This is very similar to the filament in an incandescent light bulb. When a high amperage current is circulated through the filament, it gets very hot. So hot, it creates a cloud of free electrons. We call this cloud of free electrons the space charge. That's because these electrons, or charged particles, are now out in space. The process of heating the cathode to create free electrons is that process we call thermionic emission. There is a limit to the number of free electrons that can be created at the cathode. As we increase the MA, more and more electrons are created at the filament. But there is a limit. At about 1000 MA, the space charge becomes so high that no more electrons can be forced out of the filament. This limitation has a name. It's called the space charge effect. And for this reason, 1000 MA is the effective limit of the MA that can be used in the X-ray tube. Some X-ray tubes have an MA limit that is a little higher, some have a limit that's a little lower. Many X-ray tubes actually have two cathode filaments. These are called dual focus tubes. The word dual just means two. The small filament is about 1 centimeter long, and the large filament is about 2 centimeters long. The small filament is used for small MA only. It cannot tolerate large MA because it has a small heat capacity. It would get too hot and possibly break. The small filament should only be used for small body parts because it can only be used for small exposures. So the small filament has some limitations, but it also has one big advantage. The small filament creates a very narrow and tightly aligned electron beam, and at the anode, it becomes a narrow, tightly aligned X-ray beam. This results in high spatial resolution. The large filament is just the opposite. The large filament creates a large, poorly aligned electron beam, and at the anode becomes a large, poorly aligned X-ray beam. And this results in much lower spatial resolution. But it's not all bad for the large filament, because the large filament is so large, it can be used for large MA. This is important when imaging large body parts that need large exposures. These cathode filaments sit inside of what we call the focusing cup. The purpose of the focusing cup is literally to focus the electron beam. The electrons are negatively charged, and so without the focusing cup, they would try to spread apart and repel each other in space. The focusing cup is negatively charged, and so it repels the electrons and presses them back together in a tight electron stream. Why do we care about this? Because of spatial resolution. A narrow or tightly aligned electron beam eventually becomes a well-aligned X-ray beam. And that's part of what gives us good spatial resolution or sharpness in the X-ray image. The next major component of the X-ray tube is the anode. This is where the X-rays are actually created. There are two types of anodes, rotating anodes and stationary anodes. Each anode type has advantages and disadvantages. Let's start with talking about stationary anodes. The anode is literally stationary, so that electron beam is focused onto one small area on the anode. This also means that all of the heat is focused onto one small area of the anode. So what does that tell us about stationary anodes? The design is very simple, which is good. However, these anodes have very low heat capacity, which also means we can only use them for very low exposures. This just doesn't work for general radiography. So outside of dental X-ray machines, stationary anodes are not common in medical radiography. With rotating anodes, the anode is literally a rotating disc. This has the effect of spreading out those electrons over a much larger area and significantly increasing the heat capacity of the X-ray tube. Rotating anodes are essential for general radiography. So what can we say about rotating anodes? We can say that they are a little bit more complicated. However, they have a very high heat capacity with that large focal track, and because of that, they can be used for high exposures. So what exactly turns a rotating anode? This is what we call the induction motor. The induction motor is an important part of these rotating anodes. They can't rotate without them. The induction motor turns the anode without actually touching or contacting the anode. That's why it's called the induction motor. It induces the anode to spin. There's three major components of the induction motor assembly. To start with, we have the stators. These are electromagnets surrounding the rotor. They're activated in series to induce the turning of the rotor. And that's the next component. We call this part the rotor. The rotor rotates. It's the tube shaft that's attached directly to the anode disc. And then the last part is the bearings that are in between the rotor and the rest of the X-ray tube. The bearings are low-friction spheres that allow for free rotation of the rotor. During the prep phase of an X-ray exposure, you can actually hear the sound of the rotor turning on these bearings. So that's an overview of the major components of an X-ray tube.